Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss law of increase of entropy with examples. Let's begin. Let us consider an isolated dynamic system. Here is the isolated dynamic system. That consisting of large number of particles. Since the system is an isolated system, hence the particles of that of system can interact with one another but not with the surroundings. The particles are interacted with each other inside that of isolated system but does not interact with the surroundings, as we treat that one is the isolated dynamic system. There is no exchange of energy of the system with the surroundings. In other words, we can say no energy can enter or leave to that of system. That is why we say that is the isolated dynamic system. The particles are interacted within themselves inside that of system, not to that of surroundings, and energy can't exchange in between the system and surroundings. That means there will be no such flow of heat in between system and surroundings. This is the isolated dynamic system. Okay. When all the parts of the system are at the same temperature, all the parts of the system at same temperature, what happened here? At same temperature, then the system is said to be thermal equilibrium. Then that system we can say that is thermal equilibrium. Means all the particles have same temperature. In this state, the system will be in the state of maximum probability. At that of thermal equilibrium, that system achieve maximum probability. Maximum probability, or that we can say that is in the most probable state. We know that the state, even at small deviation from the state of maximum probability, has negligible probability. If a state has maximum probable state, if some deviation to that of maximum probable will occur, we can say that is very negligible in probability. So in this case, if we consider, if we take x be the fractional deviation from the state of maximum probability, from the state of maximum probability, and the term P maximum said to be the probable of, that is the probability of most probable state. and Px is the probability of a state at a small deviation x from the state of maximum probability. X is the fractional deviation from that of maximum probability, Px is the probability at that deviation. Okay, so that is the probability of a state at a small deviation x from the state of maximum probability, from the state of maximum probability. Now, if we draw a graph in between Px, let we draw a graph between Px by Pmax versus x, graph between Px by Pmax versus x. What we see here? This is the graphical view. Here x in that of x axis, here Px by Pmax along y axis, then the graph looking like this. Here let we consider a point M. This is the maximum probability, here that is the Pmax, that point is the Pmax, Pmax is here. So what we see in that of graph, the graph between Px by Pmax versus x, the point M represents a state of system which is very close to most probable state. Point M stands for what? That is, that represent a state of the system which is very close to most probable state. Which has negligible probability. Negligible probability, it has the point M here. Now let the system is in an in equilibrium state, that is represented by that point M. Then due to collisions between the particles, the system will quickly come to the state of maximum probability. Therefore, since S be the entropy of the system, that is why S will be entropy of the system, entropy. Here entropy of the system S is given as, that is K log W of base E. S is the entropy of the system, K is the Boltzmann's constant, W is the thermodynamic probability. that in case of what, when that state is in equilibrium, what happened here, as W increases, S also increases, since S is directly proportional with W. When the system comes back to the state of maximum probability, W will become maximum, hence S will become maximum and constant. When W will be maximum, then S will be maximum and becomes constant. And here, therefore, in thermal equilibrium, here we consider in that of maximum probability case, it will be thermal equilibrium. So, what happened in case of that thermal equilibrium? In thermal equilibrium, the change of entropy will be 0. In thermal equilibrium, what we have? In thermal equilibrium, the change in entropy del S, that is the change in entropy. Change in entropy will be 0 here. Here, this is the entropy of that of system. When that is in inequilibrium state, what happens? W will be maximum, accordingly S will be maximum, and that achieve the thermal equilibrium state. Here the change in entropy will be 0. Again, as the system moves from inequilibrium to equilibrium state, when that system moves from inequilibrium to equilibrium state, this happened for what? This happened for inequilibrium state. Here is the inequilibrium state. In equilibrium state, all these things are happened. This is for in equilibrium state. Again, in equilibrium state, what happened? In equilibrium state, so this is the in equilibrium state. So in equilibrium state, what should be the outcome of that of entropy? As the system moves from inequilibrium to equilibrium state, the thermodynamic probability W increases, and hence the entropy accordingly increases. Once the system attains that of equilibrium state, it can't go back in inequilibrium state. Once the system achieves the equilibrium state, it can't go back to an inequilibrium state. Hence, that process is said to be irreversible process. Due to that equilibrium state cannot further proceed to inequilibrium state, that's why that type of process is said to be irreversible in nature, and that is said to be irreversible processes. All the natural processes are irreversible processes. For an irreversible process, the change in entropy is always greater than 0. So, in equilibrium state, what happened? The procedures like that does not change to inequilibrium state, and which is the form of irreversible process. Irreversible process, and in case of irreversible process, the change in entropy, that is del S, is always greater than 0. Here is the reversible process. In case of thermal equilibrium, the change in entropy will be 0. Here is the irreversible process, when that state transform to inequilibrium to equilibrium state, and further that does not transform from inequilibrium state. That is why it is said to be an irreversible process, and at irreversible process the change in entropy will be greater than 0, that is always increasing. This is the law of increase in entropy. This is law of increase of entropy. This is the law of increase of entropy. Means in nature, entropy is always in increasing manner. Since all the processes in nature is an example of irreversible process. Now, we have to take some examples of increase of entropy. So, let examples number 1, say transfer of heat, and second law of thermodynamics. Second law of thermodynamics. Later we have to discuss what is the transfer of heat and the second law of thermodynamics. So, we have to take two bodies. Let this is a body, that is another body B. It has temperature T1, it has temperature T2, and T1 is greater than T2, means that one is the hot body, that one is the cold body as comparison to A. Now, bring the two bodies in contact. When these two bodies are contacted with each other, what happen? Heat will flow from body A to body B till the bodies are at the same temperature. When these two bodies acquire the equilibrium state, then there will be no such flow of heat from A to B. In this stage, the two bodies will be in thermal equilibrium. Since the thermodynamic probability, which is said to be W, which is maximum at equilibrium state, in previous section we studied maximum probability at thermal equilibrium conditions. Here that two bodies are said to be thermal equilibrium. Now the temperature of A and B will be same, and when these two are contacted with each other, at that case we said to be the thermodynamic probability, that is W, will be maximum, since it has in the state of thermal equilibrium. So, during the process of transfer of heat, thermodynamic probability W increases and then becomes maximum at equilibrium state. That is why if we take the equation of entropy S, that is K log W base E, K with the Boltzmann constant, W with the thermodynamic probability. Here basically S is directly proportional with W, since thermodynamic probability maximum in case of thermal equilibrium, these two bodies are now at thermal equilibrium, at thermal equilibrium, that take the maximum probability, that takes maximum probability. And according to our equation, that thermodynamic probability direct proportional to entropy. Here, since it achieves the maximum probability, that means the entropy will be maximum. Hence, the entropy S also increases during that transfer of heat from a body at higher temperature to that of body at lower temperature. Since we can't go back from state of maximum probability to the state of lower probability, there will be no such possibility to become maximum probable to lower probable. As before we studied here, we can't transfer it reverse. That means we can't proceed from inequilibrium to equilibrium or equilibrium to inequilibrium. That is not a reversible one. That is the same one. we can't proceed from maximum probability to that of lower probability, or lower probability to that of maximum probability. And therefore heat transfer is an irreversible process. So that process leads to be what? Irreversible process. Means heat transform from higher temperature to lower temperature, but not lower temperature to higher temperature. Hence, when two bodies at different temperatures are brought in contact from one another, heat can't flow from a body at lower temperature to a body at higher temperature. That's why we can say heat can't itself flow from a body at lower temperature to a body at higher temperature. From this conclusion, what we draw? Heat cannot flow itself from a body at lower temperature to a body at higher temperature. Which is the statement of second law of thermodynamics? Which is the statement of second law of thermodynamics? Hence, second law of thermodynamics, that second law of thermodynamics is the consequences of the law of increase of entropy. That is the consequence of law of increase of entropy. Law of increase of entropy. So here we conclude transfer of heat and second law of thermodynamics to the law of increase of entropy. Now take example number 2 here. Expansion of heat. An example of increase of entropy, law of increase of entropy. Example number 2, that is expansion of gas. Expansion of gas. How gas expands? Consider a vessel which is divided into two halves. We take a vessel, that vessel is divided into two halves. Here is the first half, here is the second half, and that divided with the help of a removable partition. That is, the removable partition is here. A removable partition means that partition can be removed. Let the whole volume of the vessel be V. That whole volume of the vessel is V. Let the first half of the volume V1, here the first half volume is V1, first half volume V1 is filled with gas, that is filled with gas filled. Second one is empty, that portion will be empty as shown in that figure. Now remove the partition. When we remove that partition, what happened? The entire gas filled within this. Here is the gases. The entire gas filled within that of entire box. When we remove the partition, the gas will expand and occupy whole of the volume V of that vessel. In this process, gas expands and its volume gradually increases. What happened here? We know that the thermodynamic probability W depends upon the number of available cells, which in turn depend upon that of volume. The available cells means that indicates the required volumes. Since during the expansion of gas the volume increases and hence number of cells increases, expansion of gas, volume increases and the number of cells also increases. Therefore, the thermodynamic probability increases. That means the thermodynamic probability also increases. What happened here? The entropy will be directly proportional to that of thermodynamic probability. Hence, we conclude that during the expansion, entropy increases. During that expansion, entropy increases. Since a process in which entropy increases is said to be irreversible, since a process in which entropy increases is an irreversible process. So, in an irreversible process, entropy is always increased in nature. Therefore, expansion is an irreversible process. Expansion is an irreversible process which is an example of law of increase of entropy. Law of increase of entropy. Okay. Next example of law of increase of entropy, example number 3, that is the diffusion of gases. Diffusion of gases. Consider a vessel which is divided into two halves. Here is the vessel which is divided into two halves with the help of, again, that is the removable partition. There are two different gases at the same temperature and pressure. That portion have a gas, that portion have another gas. Means the gas will be different, but the pressure, temperature will be same for both the gases. And let W1, that is the thermodynamic probability of that partition 1, and W2 be the thermodynamic probability of that partition 2. Here is the gas, here is the another gas, but two types of gases are same pressure, temperature. Now, if we remove that partition, what happened here? When we remove that partition, now entire gases are combined, then what should be the change in entropy or the entropy of that of particular system? First, entropy of first half S1 will be how much, that is K log W1. Next entropy of second half, that is S2, will be how much, that is K log W2. W1 is the thermodynamic probability of first half, this is the thermodynamic probability of second half. Now initial thermodynamic probability of whole gas. Let initial thermodynamic probability of whole gas will be, let W, and that will be W1 into W2. The thermodynamic probability of whole gas will be thermodynamic probability of first half gas and thermodynamic probability of second half gas. Now the total initial entropy of the whole gas. Now the total initial entropy of whole gas, that is SI, initial entropy of whole gas, that is K log probability, thermodynamic probability of whole gas W. Now K in place of W, that is W1 into W2 base E, log AB, that is log A plus log B, that is K log W1 base E plus K log W2 base E, or SI is equal to K log W1 base E, that is S1, here is the S2, here is the S1 plus S2. Now when we remove that partition, the gases will diffuse into each other and both the gases will occupy whole of the volume of the vessel. Since in this process volume of both the gases increases, here the volume increases, hence their thermodynamic probability also increases. Since the volume of the whole gases increases, that's why their thermodynamic probabilities increases. Let us say the thermodynamic probabilities are transformed like W1 to that of W1 dash and W2 that of W2 dash. After diffusion, then we can say here after diffusion, what we find, that means W1 dash is greater than that of W1 and W2 dash is greater than that of W2. Here W1 dash and W2 dash are the thermodynamic probabilities of the respective gases after diffusion. Okay. Now therefore the total final thermodynamic probability after diffusion, total final thermodynamic probability after diffusion will be how much, that is W dash is equal to W1 dash into W2 dash. Since we know W1 dash W2 dash is greater than to that of W1 into W2, that is after diffusion the thermodynamic probability is greater than that of before diffusion, and therefore the whole thermodynamic probabilities after diffusion W dash is greater than of thermodynamic probability before diffusion. Therefore the final entropy of the system, therefore the final entropy of the system, that is S F final that is K log W dash base E. Since W dash is greater than W, so what happened here? We can say here I write since W dash is greater than W, so we have SF is greater than SI. Entropy of final is greater than entropy of initial. So the entropy before diffusion is lower than the entropy after diffusion. So entropy here increases. That's why what we conclude, hence entropy increases in diffusion of gas. In diffusion of gas, and therefore diffusion of gases is an irreversible process. Therefore diffusion of gases is an irreversible process. Which is an example of law of increase of entropy. Law of increase of entropy. Okay. This is the diffusion of gases. So with the help of this video lecture, we understand what is law of increase of entropy. We say that is law of increase of entropy, and examples of law of increase of entropy. First example, transfer of heat, and second law of thermodynamics. We conclude that once. And second example, that is expansion of gas, and third one, diffusion of gases. So with this useful and informative notes, let me wind up this session. Thank you.